My name is Dan Lidral Porter. I work at Puppet Labs here in Portland, and I'm a huge fan of generative art. So generative art is art that has been produced in whole or in part by an autonomous system rather than directly by a human being. So for example, this could be cutting up an existing text and rearranging it at random to get a new text. You could compose a song by interpret, say, the digits of pi as musical notes. Or you could build up an image by running a physics simulation of charged particles and tracing their paths. And the reason that I love generative art so much, especially computer generative art, is that I think it's a great way to build your computer programming and mathematics skills through iterative experimentation in a process that looks remarkably similar to goofing off. And the iterative experimentation part is key. I mean, this is one of the things we all like about Lisp, right? We get a workflow that has a near instantaneous feedback loop. So it's really easy to try something out and see what happens. And trying out a lot of things and seeing what happens really quickly is a great way to build understanding. And further than that, it's really fun to do. When there's no downtime, you're never twiddling your thumbs waiting for a computer. You just keep at it, and that's a great way to do a lot and learn a lot. So my agenda here tonight, first, I'm going to introduce you to a particularly rich vein of generative art known as iterative function systems, or IFSs for short. I'll show you how IFSs are defined and used, and introduce you to my favorite IFS, the de Jong IFS. Once you're familiar with how iterative function systems work, we'll start to play around with them by exploring their parameter space. And if you're not familiar with that term, I'll define what that means. I'll show you some problems that arise when we explore the de Jong IFS's parameter space in particular, and I'll present a tool that I wrote to help with this problem, the Many Worlds library. So I don't have much time, so let's get right to it. Iterative function systems. So to have an iterated function system, you need to start with a function, surprisingly enough. And the salient feature of this function is that its domain and its range have to be the same thing. That is, it takes inputs from some set A and gives you back more members of the set A as output. And that's what lets us iterate it, take the output and feed it back into the function as input. All of the examples I'm going to show you will be two-dimensional IFSs. So the functions will all be from R2 to R2. It's what mathematicians call R2 and what normal people call a flat surface. So this is an IFS function, the SIFS function. It takes one point as its only argument, a two-vector with x and y elements. And it returns one of 3 points with equal probability. That's what the rand nth part is doing. The first point it can return is relative to the input point. It has half the x value and half the y value. So it's halfway on a line between that point and the origin. The second point it could return is, again, that halfway point, except this time it's shifted over by half a unit and up by half the square root of 3. And the last point it can return is, again, that halfway point, except only shifted horizontally by 1 unit. So the 3 points are either a halfway point shifted over and up, or a halfway point shifted entirely over. So we're probably going to get some sort of triangular structure when we seed this with some value and then run it thousands and thousands of times. And when we do that, this is the shape that emerges. The Sierpinski triangle. Isn't that cool? I think that's really cool. Like, all that we did, no, don't clap. I didn't make this up. All that we did was define, a really short function, like it's short enough to fit in a tweet, which is the standard of shortness these days. And we got this really complicated structure out of it. And this is why I like using IFSs a lot in generative art, is you tend to have these properties that you get really complicated behavior out of a very succinct function definition. So moving along to the de Jong IFS. This is the de Jong IFS function. Again, we just take 1 point as input, and this time we always return the same kind of point. We don't have options, but it's a little more complicated. Now, the components of the point that we return are the differences between some trigonometric functions of the input points components after we multiply them by some parameters A, B, C, and D. And we're going to restrict the parameters to always be within the range from negative pi to pi. So if we were going to go ahead and graph this, we don't actually know enough yet to plot it. I mean, before with the Sierpinski IFS, because we were having the components each time, we knew that the things that we added to them were essentially the limits. And so that defined how big that our graph was. But with the de Jong IFS, we don't know its range yet, so we don't know how big to make the space to plot it. And if we choose wrong, then we won't even see the IFS at all, or we'll be zoomed in on some part of it, or it'll be some tiny point at the middle of the frame. So we have to figure out what the range is, and we'll do that by simplifying the equation a little bit. We'll replace the inputs to the trigonometric functions with generic variables alpha, beta, gamma, and delta. And you might know about trigonometric functions is that no matter what their input values are, we're always going to get out of them a number between -1 and 1. So by replacing the trigonometric functions with their minimum or maximum outputs as necessary, we can figure out what the ranges are. So the maximum value will be 1 minus -1, or 2, and the minimum value will be -1 minus 1, or -2. So now we can go back to our plot, and we can add limits on the ranges, and we're all set to go, right? Well, not quite. We haven't defined the values for our free parameters. We had those parameters A, B, C, and D in the function definition, and we can't do math on letters. We need some numbers. So I'm going to just pick some parameter values. Don't worry too much about what the actual values are. I just pick them because I know that we're going to get a cool result out of this. And so we'll seed this with a few thousand random points, and then each frame we're going to add a few thousand more points in the de Jong IFS and see what sort of shape builds up. Pretty cool, huh? I mean, I don't know what you were expecting, but the first time I saw the de Jong IFS, I was not expecting this. We have a really complicated shape with a whole lot of detail in it, and more detail emerges as we continue to plot more points. We get some fine strands that stretch around the range that only show up after we've plotted it for a little while. And I just find this to be visually beautiful. Now, we've only made one particular instance of the de Jong IFS because we just picked some parameter values more or less at random. And if we change those parameter values, then we're going to get a different shape. Pretty neat, huh? I mean, it's got some similarities to the previous shape. There's still a bunch of sine-like curves that are composing this, but they're in a totally different arrangement. And we still see it has the same property of having detail that only gets revealed as we plot more and more points. And we only end up plotting on the order of a few million points at the end of this image. If we let this run for a long time with a few 100 million or a few billion points, and we add in a color ramp based on how many points have hit a certain pixel, then we get an image like this. And again, all of this came out of a really succinct function. So let's take a step back because we're about to go into parameter space. So what parameter space is it's the set of all possible values of the parameters of a system. So in the de Jong system in particular, we had those 4 parameters A, B, C, and D. So let's start building up our parameter space. We start with just a line representing the value of the parameter A. And then once we add in parameter B, we end up with a square because we have 2 degrees of freedom. We can change parameter A whether or not we change parameter B. But of course, we're not done. When we add in the C parameter, we're up to 3 dimensions. We have a box. And then when we add in the D parameter, we're up to a tesseract or a hypercube, which is what happens when you take a cube and then you add in a whole bunch more cubes off in this direction you've never encountered before in your life. So we've only sampled from 2 points within the de Jong IFS's parameter hypercube. And in each point that we sampled, we saw a different shape for the de Jong IFS overall. And once we're aware that we're sampling points from parameter space, one next approach that you might think of is, well, why don't we define a path through parameter space rather than individual points? We'll define like a Bezier curve or something, because that is easily extendable to 4 dimensions. And then we can move along in parameter space. And at each point in parameter space, which will be a frame of our animation, we'll go ahead and plot out the de Jong IFS and see what happens. As we move through parameter space, hopefully we'll see the de Jong IFS changing in some way as well. So I don't know about you, but thinking in 4 dimensions kind of makes my head hurt. So we're going to pick some concrete values for the C and D parameters, which collapses our parameter space back down to 2 dimensions, which is a lot easier to grasp. So now we animate along this line in the AB plane of parameter space, and we see that the de Jong IFS animates as well. And it animates, it's really great and kind of surprising that this happens, that we get a smooth animation in the de Jong IFS when we do a smooth animation in parameter space. When I first found this out, I made a whole bunch of videos like this one. This is with a few more points, some nice blending modes, and at a higher frame rate, but the basic idea is the same. Now, when I made a bunch of these videos, one problem that I ran into is that you can find a lot of paths where the de Jong IFS does something like this. It compresses down and compresses down and compresses down until the entire system just is in a tiny little point or line, and that's not very interesting to look at. So now we have this problem of like, how do we find the good portions of parameter space, and how do we stay in them and avoid these boring portions where it's not very interesting to look at? Well, for reasons I won't go into depth about here, some mathematical characteristics of the de Jong IFS make this a little hard to do. It defeats a lot of simple heuristics that you could come up with. There are always some points tending near the edge of the images, so it's hard to make a bounding box around all of them. And more complicated heuristics, like say, oh, if 75% of the points are close together, then we know this isn't very interesting. Well, that requires sorting the points geometrically, which gets to be very expensive. And what I was using these for is, I was in college and I was doing visual performances at dance events. So I was trying to project something interesting on the screen 30 times a second, responding to the audio input. And these more complicated heuristics interfere. You can't do that at 30 times a second, especially since you're trying to sample as many millions of points as possible in order to get some good detail in the de Jong IFS while you're doing this live. So that led me to come up with the Many Worlds library. And the basic strategy behind Many Worlds is that the most reliable way to know if some path or point in de Jong IFS parameter space is going to be visually interesting is you kind of just have to try it out and see if it is. And Many Worlds lets you do this by managing the curve that's used when we're animating the de Jong IFS. So we have some curve, we're moving along it within our sketch, within our program, but that curve has some fixed length. And eventually we're going to get to the end of it, and then we need to pick a new curve. And so what Many Worlds lets you do is allow us to preview many possible new curves and select the best one, at which point we can move ahead up until the next curve's endpoint and repeat the process over. So when you get Many Worlds all set up, you get a control console that looks like this one. Let's start. At the top, you have some timeline controls that allow you to scrub through the timelines of all of your different potential paths or worlds. And you can see how each world responds at each point in time. And when you, so you can scrub forward and backward. You can just play. You can change the speed at which you're moving through time. And once you've found a path that you like the best, you can go ahead and select it. So I think right here, I'm about to select the middle one. And once that happens, it resets all of the other worlds to have used that point retroactively. And then you can move along ahead up until the point which they've all reached the end of that curve and each pick different new ones and again diverged in their behavior. Now, I want to close with some salient points about how the Many Worlds library works. And the first is that it's just a quill library. So if you have some quill sketch and its state is easily reducible to some collection of numbers, it should be pretty easy to use many worlds. And then you get this control console with the ability to interactively explore the parameter space and build up cool behavior incrementally for free. And the second is that all of this is happening over HTTP. So you could use this in live performance by having, say, one computer that's running the presentation world that's actually hooked up to the projector. And you can have another one that's running all of your different preview worlds, and they're communicating over HTTP. So you can do a lot of preview generation without worrying about bogging down the live performance. And finally, this, I like to think that it continues in the tradition of Lisp in the vein that it facilitates interactive exploration, and it lets you do things incrementally. Like before I thought of this, I would just generate a lot of paths, and then after the fact, go through and see if each one was interesting or not. And this lets you build up one incrementally, which is a lot faster. So the Many Worlds library you can find up on GitHub under my GitHub account, which is aperiodic. I'm going to be at the party at Puppet Labs later tonight, so you can talk to me there if you have any questions, or if you just want to talk about generative art, which I always love to do. And you can also reach me on Twitter, where my handle is @aperiodic, if that is more your jam. So I hope that this has been entertaining and maybe informing, and have a good night.